dear colleagues. Thank you so much. I'm really pleased to give a talk here. So, well, yeah, I'm going to talk about the Schrödinger's equation, so I'm going to switch gears and talk math. Well, I hope it's not going to be that complex. So first off, you said, you'll just ask me, Schrödinger's equation and magnetic fields, like, are you kidding me, right? So, because the solution is long known. Landau solved this problem long ago, so what should we discuss here right now? All right, it's easy and not that easy at the same time. First off, let me just give you a brief outline of my talk. So first, I'm going to talk about the twisted states. It's something that is really interesting and which attracts a lot of attention right now, twisted quantum states, and they're tightly connected to these magnetic fields and electrons and magnetic fields and such and such. Then I'm going to talk about like which exact problem we're going to solve. And then we talk about a bit of a so-called rectification theorem. It's something from a differential equations, but I'll try to make it simple. And then I'm going to talk about some mappings and then the application actually to the so-called Landau states or to the states of the electron and the magnetic field. So what kind of a new insights we can gain out of this math that I'm going to talk about right now. So first off, the twisted states. What kind of a beast is that and what I'm going to talk about. So the twisted quantum states are kind of very simple. So we know that there's such thing as a plane wave. The plane wave has a plane wave front, right? So it's known to almost every physicist. But along with the plane waves, there are also cylindrical waves. It's just a different solution to the wave equation in 3D. But the thing is that they're kind of like completely different from the plane waves. And if you look at the wave front, so the wave front of such a wave is a spiral. And it's a kind of funny and distinct feature, but so what's about it? So along with this like spiraling wave front, you have a so-called angular momentum, a projection of the angular momentum. So indeed, this wave have a kind of twist, so it kind of rotates along the propagation axis. So for instance, if we're talking about the light, if I illuminate with this light some small particle, we all know about the pressure of the light, right? So if you illuminate something with a light, then the light has the pressure, right? You can sense the pressure of the light. But if you illuminate something with a twisted light, we'll sense not only the pressure, but the momentum. So it will rotate the object that you illuminate. That's a kind of really kind of fun and interesting feature of this particular state. Interestingly enough, the photons are not the only waves that we know, right? And just because of the duality, all particles, because particles are waves, can have these features. For instance, electrons also could be considered as twisted waves, and it's all the same. It's the same as light. So if you look at the intensity profile of such state, so you'll see that they kind of have these donut shapes, and depending on the quantum numbers, actually the amount of the momentum, of the angular momentum that this state carry, have a different structure. So it could be like one donut or like several donuts and such and such. Here I have two references. Just if you'll have access to these slides, you can read more on that. And you can, there are two nice reports that have a really brief reviews of all that stuff. Both states, in both cases, the waves are explained by the means of these functions. They're kind of like a bit scary, but like, look, so we have this like transverse part, which is in cylindrical coordinates, it's just the Laplace operator, and we have this longitudinal part, which is just the first derivative by z. If you look at this formula, it will probably remind you of the Schrödinger's equation, because this part is just the momentum operator, and this is some kind of a time derivative. The solution is like that. So it has these Laguerre polynomials, these exponents, and everything depends on z coordinate here. So you have these size here, and you have this so-called the wavefront curvature, and you have a phase factor, which is here. So the Landau states, like long ago, Landau solved this problem for the electron in the magnetic field if you have a uniform magnetic field, and it's kind of not really connected to what I've showed you before, because that was something different, right? But if you look at the equation and at the solution of this equation, it basically resembles the same formula as for those twisted states of light and of the twisted free electrons, if you want so. So basically, the Landau states and twisted states are kind of the same beast. And that's kind of the question. So how you connect those two things together, and that's what I'm going to talk about today. So how you connect kind of old stuff that is known with some new ideas and some new, well, research field, which is kind of booming right now. One important feature that I'm not going to really talk about today, but I really want to mention, that the orbital momentum is so-called topological charge. So to make it brief, what the topological charge is, it's some sort of a number that if you put into your state, into your quantum state, it will never disappear. So it will always be there. So it's some sort of a structural, if you want so, structural number that you can, well, you can only like either insert or remove. So it kind of responsible for the shape and for the again, the transfer structure of your wave. So once it's in, you can never remove it out of. And the orbital momentum and the topological charge, as Barry told us, it's kind of the same. Well, let me switch to the problem and let me talk like what we're trying to do right now. So actually, now if we know that in a free space, it's a twisted wave, and inside the magnetic field, it's a Landau state, how we can bridge those two states together and how we can answer the question, like whether it's possible for the electron to transit from the free space, if it's twisted into the magnetic field and being captured directly into the Landau state. Well, first off, we'll start from the Dirac equation. And we know that the Dirac equation could be reduced again to the Schrödinger's equation if the field is uniform. And this transformation is called Foldy-Watt-Heise transformation. But let me just say that. So you can do like some trick, and you can again transform your Dirac equation again to the Schrödinger's equation that I showed you on my first slide. And in the end, what we're going to do, we're going to solve this problem. And this problem is kind of well known. So it's a harmonic oscillator. You have like momentum squared sum, coordinate squared sum, and the projection of the orbital angular momentum operator, which is basically the which connects those two oscillators. So how are we going to do it? One more thing. Previously, I showed you that it was just a harmonic oscillator, but just because I can insert those terms here. Those are the dissipation terms, so I can actually account for the dissipation in the quantum problem as well. Just for the generality, because I mean, this problem could be solved as easy as the previous one. How are we going to solve it? Well, interestingly, the solution of this quantum problem goes back to, well, a classical idea, and this idea is so-called the rectification theorem. It's you can find it in a well-known book by Vladimir Arnold. It's on the differential equations, and Arnold says that in his book that this idea goes back to Newton. So basically, the solution of a quantum problem goes back to Newton. Okay, so what's the idea? Okay, the idea says that if you have a, say, differential equation like that, you can make a substitution of variables such that in the new variables, for instance, here it's t and y, all solutions will be just constants. Basically, you rectify locally the vector field of your equation. Okay, it doesn't give us much, right? So you have to know the solution of your equation, and then you can do the substitution. Well, yeah. But if I'll switch to, well, a slightly more complex problem, then what can I do? So I'll take the harmonic oscillator, do a substitution, and this harmonic oscillator with the friction and the force could be reduced to just a free particle motion, right? Look, this equation corresponds to the Hamiltonian. And this means that this transformation transforms the Hamiltonians. And this is interesting, because in the quantum mechanics, we work with the Hamiltonians, with the Hamiltonian operators, right? So that means that this transformation can transform Hamiltonians. And if I'll just add hats to these H, to these H functions, there will be operators. And we can go to the quantum mechanics as easy as that. So this trick is called the quantum Arnold transformation. So basically, I'll do the substitution and pose a question: can I transform a Schrödinger equation for the free particle to the Schrödinger's equation of the harmonic oscillator? Well, the answer is yes. So first, I'll do the substitution that I showed you before. That's the solution of the classical equation. But in quantum mechanics, well, you have to account for the phase of the wave function. And interestingly enough, just because like everything that is happening when I do this substitution, I have the shift in the momentum, then I can easily find the phase. And this trick is called this guy is the gauge potential, and this is the phase caused by the classical gauge potential, which again comes from just the classical transformation. So finally, the transformation will look like that. So U1 and U2 will be the solution to this harmonic oscillator, to the equation of the harmonic oscillator, a classical equation. So it's not a quantum equation. And I'll do this transformation of time and coordinate, and will account for the phase factor that appears just because I shift the momentum. And this operator will transform. Okay, so I jumped too fast. This operator will transform my free equation into the harmonic oscillator equation, Schrödinger's equation. Well, I can go back and forth because like you can show that this is a unitary operator and this operator is unique. So that means that there's a one-to-one correspondence between those two systems, which is kind of cool. So you can make a step further and connect two harmonic oscillators, and by just composing those two transformations. So H here is the harmonic oscillator with the omega-1, and HT it's with the omega-2 and the different friction coefficients. So if you compose them, you can build a composed transformation, which we call Yermakov transformation. And here you have a very simple equation for this B coefficient, which basically is the main coefficient in this transformation. So this means that now I can, if I know the solution inside the magnetic field or say in free space, I can easily solve the problem by the transformation. So if I know the wave function, then I just need to solve a simple classical equation, and I know the evolution of my state. And this is, well, as simple as that. So before that, we started from the non-stationary quantum problem, and we were able to reduce it to a solution of a, non-linear, but a very special non-linear equation. This equation, by the way, is called Yermakov equation, and it allows exact solution. So it's so-called integrable equation. So despite the fact that it's non-linear, you can solve it exactly in many special cases. The Landau states, what we can learn about the Landau states, long known states, that was derived by Lev Davidovich. So just to recall what those states are, that's the harmonic oscillator, the connection. So the magnetic field is constant, it's time independent, and the solutions could be written down in this form, as I showed you on one of the first slides. Instantaneously, if I will map this system on itself, just for fun, you'll see that Landau states are not the only solution to the Landau problem. And you have, on top of just stationary states, which was derived by Lev Landau, you have non-stationary states that looks slightly different. So what's the difference? The difference is that the average values calculated on these states will differ by this B coefficient. And B, again, is the solution to this Yermakov equation, which is not necessarily constant. So it basically depends on time. So this problem allows, say, oscillating solutions. If the solutions oscillate, then the classical multiple electric moments oscillate as well, and in this case, those solutions must radiate. Let's look. Let's look at the example. So what is happening? So if I'll just solve this equation, then this parameter that describes basically the size of my packet. So it shows that in free space it expands, then it oscillates inside the magnetic field, and then if I'll choose the parameter the right way, I can capture the packet exactly into the Landau state, but that's a very rare case, so it's practically impossible to capture the packet. So the oscillations will always occur. As for the energy looks always also funny. So if the packet goes from the vacuum into the lens, the energy goes up, and that's because as I said, just because you have the oscillations, and the oscillations will cause the radiation. So, well, I know that was a bit fast, but to conclude, what is the point of all these tricks? So, look, we started from the quantum problem, right? So, and I briefly showed you how a very simple idea of Newton, right, could be applied to the quantum problem, and shows you the essence of the evolution of the quantum problem, which is actually classical, right? So we've learned that the solution of this problem could be found through the classical equation, which is a bit, which may seem complex, but, it's just one simple equation instead of the Schrödinger's equation. And this simple equation is just for one parameter. That's basically it. So I want to mention that we've recently done this research with my student, and if you want to learn some details about that, you can read this article. Other than that, thank you so much, and I'll take any questions right now.